Let me welcome all of you to this public talk today by Professor Harald Fritzsch. It's a great honor for us to have Professor Fritzsch come and participate in this symposium and agree to give this public talk. As you know, Standard Model has two parts, the electroweak theory and quantum chromodynamics, which is the SU3 part of the SU3 cross SU2 cross U1. And it's Professor Fritzsch with Gell-Mann who proposed a gauge theory of strong interactions, which today is known as quantum chromodynamics. And it's indeed great that we could have Professor Fritzsch himself give a public talk on quantum chromodynamics. Professor Fritzsch has done many significant contributions in particle physics. For example, with Peter Minkowski, he proposed the SO10 grand unification for the first time. And this is a very valid theory for grand unification. And in this theory, neutrinos do get mass. We've had a lot of discussion about it, and this is something nice about it. In 1979, Professor Fritzsch developed theory of mass matrices of quarks and leptons, in which certain items are zero, or this texture. So this became a very important area of work, and a lot of development took place. Professor Fritzsch worked on composite models of quarks and leptons and mass matrices of quarks and leptons and weak decays of heavy quarks, cosmology, fundamental constants, among other things. And too many significant contributions for me to list here in detail. He is also the author of several very popular and famous books. In fact, there are so many titles if you go to Wikipedia. One of the early ones was Quarks. And he has a book on escape from Leipzig, where he describes his escape from East Germany and how his QCD ideas evolved, the reasons and things. He will give a public talk also on Wednesday at 5:30 on the escape from, on Friday. Sorry, thank you for correcting. On Friday, escape from Leipzig. An eminent personality like him gets several awards. I will absolutely not list them here. I will just say that I was so impressed by his work that when I graduated, when I finished my PhD and was looking for a postdoc in mid-1980s, working under him was my first choice. The work was so impressive that QCD was such a great theory for me, so nice, and composite models and these things just took me away. I wanted to work with him. Unfortunately, it didn't materialize, but I'm fortunate to have opportunities to discuss with him. Thank you. Thank you, Professor Fritzsch. Can I kindly request all of you to take a minute and switch off your mobiles? We would not like any disturbance in between. Kindly switch off your mobiles. Thank you.
Okay, thank you very much. I will speak about the theory of quantum chromodynamics, shortly called QCD. But can we turn off this light? But otherwise, it's not very good. Yeah, so it's good. Actually, Gell-Mann had a different idea. He wanted to call the theory QHD, quantum hadrodynamics. It's also a good name. But then the color quantum number plays a big role. So I convinced him we should take the Greek name and call it QCD, quantum chromodynamics. And that has caught on. And we call it like this since 1973. As Professor Sinner just mentioned, the Standard Model consists of two pieces, the electroweak interaction and the theory of QCD for the strong interactions. This institute is now 50 years old, and the theory of QCD is actually also has an anniversary this time. It's now precisely 40 years old. It was actually first talked about at the Rochester meeting in 1972 in Chicago. So it's now 40 years and 2 or 3 months. And before I come to this, some basic things which you all know. you know that electric charges, if they are the same charge, they repel each other, like this one, and if the different charges, they attract each other in electromagnetism. And that was explained by Michael Faraday in 1850, where he introduced the concept of an electromagnetic field, which connects the two charges and provides the force for attraction or repulsion. And about 14 years later, in 1864, Maxwell was able to describe the electromagnetic interactions by his famous equations. Maxwell at that time didn't understand that his equations actually had a special symmetry. They were Lorentz invariant, but it was only realized after Einstein introduced special relativity in 1905. Now, the theory of Maxwell's equations for the electromagnetic interactions, that was finally brought together with quantum mechanics by Heisenberg and Pauli, and they created out of quantum mechanics plus Maxwell's equations the first quantum field theory, which we now call quantum electrodynamics, QED. And that is a basic field theory which is also a good model then for QCD. In QED, the attraction between electric charges, for example, the force is created by the exchange of force particles, and which in QED are nothing but the photons, the quanta of light, the particles of light, which go around back and forth and create this attractive force. Now, about the strong interactions. Around 1910, Rutherford, at that time he was already in England, he came originally from Australia, he made his famous experiments using alpha particles, and the alpha particles were penetrating through a very thin sheet of metal, and some of the alpha particles were reflected with a large angle. And that was very surprising. And finally, Rutherford came to the conclusion that could only be made if most of the mass of an atom is inside in an atomic nucleus. So then the atomic model, according to Rutherford, was a nucleus with positive charge surrounded by many electrons. So the nucleus looks like this. The proton, the particle of the hydrogen atom, the nucleus of the hydrogen atom, is part in the nucleus, but in addition there are also neutrons, which Rutherford around 1919 concluded that neutrons must exist, and they were discovered 1932. So the protons and neutrons glue together and make a nucleus. The neutron and proton were finally brought together by a new symmetry, the isospin symmetry. It is an important step by Werner Heisenberg in 1932 because he first invented the first internal symmetry. Later on, we will see that there are other internal symmetries also, but this was the first one, a very important step. In the isospin symmetry, the proton and neutron are just considered to be one particle. The particle is called nucleon, and the proton and neutron are just different manifestations of this particle. And actually they are a doublet of the group SU2, a very simple group, and that describes the nucleons. The question came up then, what is the reason why the atomic nucleon, the nucleons are brought together to form an atomic nucleus? What is the strong force? It could not be an electromagnetic force, since the nucleus consists of many protons which repel each other. So without that strong force, an atomic nucleus would immediately fall apart. But that's not the case. So what is this strong force? Well, in 1935, Yukawa in Japan had the idea that the strong force is mediated by a meson, the exchange of mesons. The electromagnetic interactions are mediated by photons. In a very similar way, he took now another particle which nobody knew that it would exist. He called it a meson that would go around. So the strong force would be produced between a proton, two protons, or proton and neutron, by an exchange of a meson, which later on was called the pi meson, or pion. And in fact, in 1947, the pion was discovered in England in the cosmic rays. Yukawa had predicted that his pion here, according to what was known about the nuclear force, he predicted the mass of this pion must be around 100 MeV. And it was found close to this, namely 140 MeV. And there are three pions, a positively charged one, a negatively charged one, and a neutral one. So that was an important step to understand the strong interactions. We see that this is not a fundamental theory of the strong interactions, but it describes a lot of nuclear physics. But in 1950, new discoveries were made. In particular, one discovered the hyperons and also the K-mesons in cosmic rays. One of the first particles was the lambda hyperon. It has a mass which is about 1100 MeV, so it's about 20% heavier than the proton, which has a mass around 940 MeV. At higher masses, finally, there were three sigma hyperons found, sigma plus, sigma 0, sigma minus. And at further higher masses, even the sigma hyperons, which are two of them, chi 0 and chi minus. The sigma hyperons are an isospin triplet. The chi hyperons are an isospin doublet. And the lambda hyperon is an isospin singlet. So together with the two nucleons, all of a sudden there were now 8 baryons. So the proton had 7 brothers and sisters. In 1950, another important discovery was made in Berkeley with at the LBL laboratory, Lawrence Berkeley Laboratory. One discovered the delta resonances. The delta resonances are excitations of the nucleon. What they did was they were shooting pions against nucleons. And then all of a sudden, there were new particles. 4 of them were found. One with a doubly charged, delta plus plus, with twice the charge of the proton. A delta plus, a neutral one, and a negatively charged one. And now these particles, all together, were grouped finally by Gell-Mann and Neumann in a bigger group, an extension of the isospin group, which is called the SU3 symmetry. Gell-Mann called it the eightfold way because of the eightfold way which you perhaps know from Buddhism. That's a picture of Gell-Mann in those days, and that's Neumann. Neumann was, they did it independently. Neumann was an attaché at the embassy of Israel in London. He was a trained engineer, was not a physicist. And he was bored with his job at the embassy, so he went to hear lectures of Abdus Salam in the Imperial College. And then he got into closer contacts with Salam, and Salam told him he should try to make to understand these new particles. And that was around 1960, and 1 year later, Neumann proposed the SU3 symmetry at the same time when Gell-Mann had this idea. In the SU3 symmetry, the 8 baryons we observe are now described by an octet. The nucleons are a doublet of SU2. and the 8 baryons are an octet of the group SU3. So this octet is described in the following way. Here you have the 3 sigmas, together with a lambda in the middle. Sigma 0 and lambda are right in the center. Then here you have the 2 nucleons, proton and neutron, and here the chi0 and the chi minus. That's the octet. The mesons, which were known at this time, were 9 mesons were known, actually only 8. The one was discovered, I think, only in 1962. But anyway, there are 9 mesons. And out here you have the 2 k mesons. In the middle are the 3 pi mesons. And in the middle also you have here in the center the pi 0, the eta prime, and the eta meson. The eta prime turns out to be an SU3 singlet, close to an SU3 singlet. And the eta is an SU3 octet. Now, another thing I should like to mention, the isotopic symmetry introduced by Heisenberg was violated, was not respected by electromagnetism, since the proton has a positive charge and the neutron is electrically neutral. So electromagnetism breaks the isospin symmetry. But the SU3 symmetry was a bit mysterious because there is no interaction, not like something like electromagnetism, which you could use to break the symmetry. So finally, Gell-Mann had an interesting idea. He said, well, the symmetry breaking, I don't know where it's coming from, but I will assume that it is an SU3 octet. And then from group theory, you can make a statement. And the statement is that Murray Gell-Mann and also at the same time Susumi Okubo, who was a teacher of Professor Sinha, proposed a mass relation which is given here. You see the lambda sigma mass and the nucleon and the chi mass are related. And this mass relation is coming just from the assumption that the symmetry breaking is an octet, and it works extremely well, within 2 or 3%. Now, another thing which Gell-Mann had to worry about, and also Neyman, is the following. At this time, it was known that there are the 4 delta resonances. Then there are 3 sigma star resonances, excitations of the sigma. Also the chi star, the excitations of the chi, with relatively high masses. The masses are given here on the right-hand side. But these are only 9 particles. But there is no representation of SU3 with 9 particles. There's an octet. And the next representation is a decuplet, which would have 10 particles. So the question is whether there is a 10th one. Well, you see already from the question mark that the hypothesis of Gell-Mann then was made that this particle must exist. He called it omega minus. And according to a similar mass relation like the Gell-Mann-Okubo mass relation, he predicted the mass of this particle to be very precisely to be 1670 MeV. Now at CERN in Geneva, they had a big machine. They could easily produce this particle, but at CERN the theoreticians didn't believe in the SU3 symmetry, so they told the experimentalists they shouldn't look for this. But in Brookhaven in the States, they started a big program because of the pressure of Gell-Mann to find this particle. And indeed, Nixamios, a Greek, somebody from Greece who was a professor then later on at Brookhaven, and his group discovered the omega minus at a mass of 1672 MeV, precisely the mass Gell-Mann had predicted. And that was a very important discovery because the existence of the omega minus implies that the SU3 symmetry must be realized in nature. It's a symmetry it's really a true symmetry. And that was also the reason that Murray Gell-Mann finally got the Nobel Prize in 1969. Now, the mesons, as I said, are octets and singlets. The baryons are octets, decuplets, and there are also singlets at higher mass, which I didn't mention. But in SU3, something is funny. In isospin, all the representations which you can think of are realized in nature by atomic nuclei. But in the SU3 group, you have the simplest representation is a triplet. In SU2, it's a doublet, and that is realized by the two nucleons. But in SU3, it would be a triplet, and there are no triplet particles in nature. And also no sextet. The sextet is also a representation for SU3. So the simplest representation is a singlet, but then it's followed by an octet. But triplets and sextets do not exist. Something very funny. And then in 1964, finally, Gell-Mann proposed that the triplet particles indeed exist in a different way. And he called these objects quarks. And at the same time, a graduate student of Dick Feynman, who worked at CERN for a year, George Zweig, had the same idea. He called them aces, but his name didn't exist for a long time. Now we call these things quarks. But Gell-Mann didn't believe that the quarks are real particles. He thought the quarks are just mathematical entities which are used for the mathematics. But he was wrong in this respect. Here you see Gell-Mann, and this is George Zweig. I couldn't find a picture. George Zweig was a young graduate student at this time. Here it looks a bit older. He is now a professor at MIT. He works on biophysics. Now the quarks are SU3 triplets, as I mentioned. The name quarks is coming actually from James Joyce. Gell-Mann is not only a physicist, also a linguist, and he knows many languages. And there is a famous book which actually is written in several languages called Finnegan's Wake by James Joyce. Sorry, that was too fast. And strange enough, on the page 383, this quotation you can find. The number 3 plays a big role in SU3, the number 8 also. And Gell-Mann knew this quotation. And since it says 3 quarks for Mr. Mark, then he calls them quarks. Gell-Mann also knew German, and he knows in the German language, you don't know it, but quark means some sort of yogurt, but it also means nonsense. People say usually, if a politician says nonsense in television, oh, he speaks quark. Quark means nonsense. But Gell-Mann nevertheless calls these things quarks. And anyway, once you have the quarks, then the proton and neutron are not fundamental particles anymore. They are replaced by 3 quarks, U, D, and S. The reason Gell-Mann didn't publish the quarks already in 1963, or he had the idea already in 1963, was something funny. Because if you make up the proton and neutron out of 3 quarks, you can easily convince yourself that the electric charges of the quarks are non-integral. They are 2/3 or -1/3 of the fundamental electric charge. And of course, that is very unusual. We don't observe in nature non-integral charges. And for that reason, Gell-Mann, when he published his small letter, a 3-page letter, he didn't send it to Fisher's letters because he was sure the referees in Fisher's letters would reject his paper. So he sent it to physics letters. And Jacques Brentke at CERN was the editor of physics letters. He got this paper of Gell-Mann, and he thought, my God, this is completely wrong. So he was about to reject it. But then he realized that Gell-Mann is a famous physicist. So he said to himself, if the idea is wrong with the non-integral charge, and I'm sure it's wrong, then Gell-Mann should be blamed and not physics letters. And if it's right, it's good for physics letters. And it was correct. It was good for physics letters. It was the most successful paper ever published in physics letters. Now, this is the structure of the proton and neutron: up, up, down, 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 up. You see easily that they have non-integral charges in order to make up the integral charge of the proton. That's now the structure of a nucleon: two up quarks and a down quark. All the atomic nuclei in the quark model are composed of up and down quarks. You don't need any strange quarks for this. The mesons are quark-antiquark bound states, and the baryons are 3-quark bound states. And you see the quark itself is not a particle, and 2 quarks together would form a sextet, and they also do not exist, only 3 quarks. That at that time was not really understood. Many physicists didn't believe in the quark model, but they couldn't believe that there is a 3-quark bound state, but a 2-quark bound state should not exist. It was very funny. Now in the quark model, the isospin is just generated by up and down quarks, and the 3 quarks generate the whole SU3 symmetry, U, D, and S. So the SU3 group is generated by the 3 quarks here. If you rotate them around, you generate the group SU3. And the SU3 group also gives now the wave functions, the structure of the 8 baryons. You see here, up, up, down makes a proton. That's a neutron. These are the 2 chi's, the 3 sigmas. And the lambda and the sigma 0 both have the wave function UDS. Now the sigma 0 is quite a bit heavier than the lambda. So the question is why, if they have the same wave function, why the mass is not the same? Well, the reason is the quarks also have a spin. And the spin structure of the sigma 0 and of the lambda are different. That explains why the masses are different. There's some sort of hyperfine splitting. The mesons are quark-antiquark bound states. Here you see the K mesons are the D bar S, or the S bar D here, or S bar U and U bar S. Here in the middle you have the eta, the pi 0, eta, and eta prime. And they are just superpositions of U bar U, D bar D, and S bar S. So it's easy to see in that picture also that it's not 8 mesons, but 9 mesons, but they split up under SU3 into an octet and into a singlet. And the decouplet wave functions are also very simple. The delta plus plus with 2 charges just consists of 3 up quarks. And the famous omega minus particle is just 3 strange quarks bound together. Now Gell-Mann, unlike George Zweig had the idea that his quarks are really physical things inside the nucleon. And Gell-Mann had the idea that the quarks are just mathematical entities. And that was the time in 1969 when I, after escaping from Eastern Germany, I went to Aspen and I met Gell-Mann and I started to collaborate with Murray Gell-Mann. And in '69 I was at Caltech and I kept telling him that at SLAC they seem to see something which looks like quarks. This is the famous SLAC accelerator, a linear accelerator, coming from the mountains close to the Pacific here, crossing the freeway from San Francisco to San Jose down here. And here you're bombarding with electrons or positrons atomic nuclei, which are the experiments are analyzed here. And what one did at SLAC was the so-called deep inelastic scattering of electrons and atomic nuclei. So what you do is an electron scatters in a proton. The proton is excited and decays and makes lots of new particles. And it's analyzed in these big detectors like this one here. This was the most famous detector which discovered the quarks indirectly by Richard Taylor and Slack and the MIT group. And one has observed at Slack the quarks indirectly. That means an electron comes in, it scatters on a quark, and then it's deflected. And if you do a detailed analysis, then you can figure out what the charges of this object is, and the charges turned out to be 2/3 or -1/3. And one also was able to measure the distribution functions of the quarks inside, so many things came out of this. So the quarks were finally observed. And it was clear the quarks are more than just mathematical entities. Now another problem why people didn't take the quark model seriously at this time is this problem with the Pauli statistics. Look at the omega minus particles. These are 3 strange quarks, and the spins of the 3 quarks are all aligned, and they are forming in S. Since this is a ground state of 3 strange quarks, the space wave function is symmetric. It must be an S wave. And then if you exchange 2 strange quarks, everything is symmetric. And that is not allowed by the Pauli statistics. And finally, in 1971, Gell-Mann and myself came to the conclusion that the quarks must have a new quantum number. And since it must be a 3-fold quantum number, index 1, 2, and 3, we called it color, because you need 3 colors, for example, in television, to make up all the colors, red, green, and blue. So we called them colored quarks. So instead of 3 quarks, we had to have 9 quarks. And these 3 colors are forming a group, SU3 of color. Oh, sorry, it was too fast. And this color we consider to be, since there was no evidence in nature that there is such a symmetry, it must be somehow hidden. So we assume that this is a completely exact symmetry. That was the first exact symmetry, non-abelian symmetry, which was realized. And then we said that the physical particles are singlets under this color group. Sorry, that's too far. Singlets under this color group. And the singlets, there are 2 ways to make singlets. Either 3 quarks, making it completely antisymmetric, which is epsilon tensor. And that would be a baryon. Or you sum over red, green, and blue, and that again is a singlet. And that would be a meson. And you see immediately a quark is not a singlet, it's a triplet. And 2 quarks are either a triplet or a sextet. And so they are also not, it can never be a singlet. So that would explain immediately why there are no sextets and no triplets, under this rule that the physical particles are color singlets. Why they are color singlets was not clear at this time, but it was just our assumption. So then a nucleon would be consisting of 3 colored quarks, a red, a green, and a blue one. For example, the proton is a blue up quark, a green up quark, and a red down quark. The colors always would change immediately here, and the total wave function of the nucleon is just a superposition of all these possibilities. Now, as you perhaps know, a red, green, and blue in optics, if you superimpose, you get white. White is not a color, it's a superposition of 3 colors. So you get a white light if you just take these together. So we called the hadrons, the mesons and baryons, we call them simply white states. These would be the physical hadrons. So omega minus then would consist of a blue strange quark, a red strange quark, and a green strange quark. And it's quite clear now because of the antisymmetry now between the colors, that now the wave function is now really antisymmetric, and the Pauli statistics is okay because of the color quantum number. There were other indications that the color actually exists. Because 1948, Chuck Steinberger, at that time he was a theoretician in Princeton, later on he became a famous experimentalist. Chuck Steinberger did this simple calculation. He assumed that the pi zero consists of a nucleon and an antinucleon, and when a pi zero decays into two photons, then just a nucleon and antinucleon annihilate in such a triangle diagram. And he calculated it, and he found indeed that it agrees completely with the experimental decay rate of 10 to the minus 16 second. But then, that was well known. But in the quark model, there is a problem that was pointed out by Stephen Adler in 1968. If you do the calculations in the quark model, if you replace the nucleons, here are the nucleons, you replace them by the quarks, then the non-integral charges would come in, and you calculate now a decay rate, which is doesn't agree with the experiment. It's a factor of 9 less, so almost an order of magnitude less. That was a big problem. And then I realized with Gell-Mann, after we introduced the color, I realized immediately that because of color, the 3 colored quarks are going around here. So it goes, in the amplitude, you get now a factor of 3, and in the decay rate, a factor of 9. So we get back now the old Steinberger result, except we have now the colored quarks here in the triangle diagram. That was another indication that color really exists. Another indication came in 1972, or actually already 1971, from electron-positron annihilation. If you annihilate an electron and positron at high energies, and then you produce hadrons, it's customary to compare this process just with the production of a muon and anti-muon. And you calculate this ratio R, which is the ratio R is just the rate for producing hadrons compared to the rate for producing muon pairs. And in the quark model without color, you can easily calculate. You just sum over the squares of the charges, and that is 2/3. It doesn't agree at all with the experiment. The experiment were close to 2.1. Actually, here are the data. And look here at low energies. These are other quarks, which I mention later. But here at low energies, it was around 2.1. It didn't work at all. But then we did the calculation with colored quarks. Of course, you just get a factor of 3, just like in the pi zero annihilation for the amplitude. Here the decay rate. And 3 times 2/3 is 2. And that agreed well with the experiment. So there were these various indications, omega minus, pi zero decay, and E plus E minus annihilation, that the color is there. And then in 1971, I was working with Gell-Mann at CERN, and in the summer of '72, we considered first a gauge theory using the color group. And that was then finally the topic of the big lecture of Gell-Mann at the Fermilab conference, the big Rochester conference at Fermilab in 1972, in September 1972. And that is the theory which 1 year later we called quantum chromodynamics. Short name QCD. I like to write it like this: a red and a green and a blue together, and both indicating the 3 colors. Now, quantum chromodynamics is a theory just like quantum electrodynamics, except the gauge group is not U1 like in QED, but it's the non-abelian group SU3. It's the first non-abelian gauge theory. The idea of non-abelian gauge theory goes back to Wolfgang Pauli, Pauli had the idea in 1953, and he used the group SU2, and he wrote a letter to the Institute for Advanced Study in Princeton, to a friend, Abraham Pijs, actually, from Netherlands. He was also in Princeton. And he described the theory, but he never published the theory because he didn't know how to introduce a mass for the gauge bosons. Of course, in QED, that's not a problem since the photon is massless. But if you want to have such a theory for anything else, like SU2 for isospin, that was in the mind of Pauli, then there are no massless particles. But 1 year later, the theory was published by Young and Mills, and also by a student of Abdus Salam. And Young and Mills, for a strange reason, didn't mention the letter of Pauli, but they knew they were reading the letter of Pauli of 1 year before. Very strange situation. Anyway, the theory was around, and we are using now this idea for the theory of QCD. The Lagrange function of QED is very simple. It just has the electromagnetic potential coming in here in the Dirac Lagrangian, and that is the part for the field strength for the photon. You just replace the field strength of the photon by the field strength of the gauge products of QCD, which we called gluons. And I didn't like the name gluons, since it's a superposition of English, clue, and on coming from Greek. So I kept telling Gell-Mann I like to call these objects chromons. Would have been a better name. But Gell-Mann insisted we call them gluons, since he had introduced the name gluon already before in a abelian gauge theory. But the name chromon would have been better. So these are the gluonic field strengths. There are 8 of them, since the gluons are in color octet. And here are the 8 gluon potentials. So it's very similar. The simplest Feynman diagram of QED is given here, just with a photon exchange explaining the repelling force between 2 electrons. And in QCD you have the same Feynman diagram, except you replace here the electric charge in the vertex for the QED by a strong charge G, which is just the coupling constant of QCD. So the coupling constant of electromagnetism is E, and you perhaps know E squared over 4 pi is the famous fine structure constant introduced by Arnold Sommerfeld in 1912, 1 over 137. And in QCD we have a similar number. It's now G squared over 4 pi. And later on I will give you the numerical value for this. Now the interactions in QCD are more complicated than in quantum electrodynamics. In QED you have just the interaction of an electron with a photon, but in QCD you have an interaction of a quark with a gluon. The gluons are described here by these wiggly lines. And you see also now there are interactions of 3 and 4 gluons. So there is a glue-glue-glue interaction like this one, or a 4-gluon interaction, and of course the original quark-gluon interaction. And these direct interactions of gluons are now very important for QCD, as we'll see in a minute. First, again, oh sorry, that was too fast. That is the structure of a nucleon. Again, the 3 quarks are bound together by the exchange of the 8 gluons. Now it is very well known, it was discovered in 1972. Actually already in 1968 by Kriplovich in Russia, but then it was forgotten. And then 1972 by Toft, and 1973 again by Gross and Wilczek and by Politzer, that such a theory has the property of asymptotic freedom, which means that the coupling constant decreases at high energies. The electromagnetic coupling constant is going up at high energies, but here's the opposite effect. It goes down to 0. And this was measured in the experiments. Here is the strong coupling constant, alpha strong, depending on the energy. These are the data from SLAC.
Here, this time, Professor Harald